And the usual first question, can people hear me? Some people can. I'll have to do with that. So I'll speak about D-tilting bundles for Geigle-Lenzing projective space. And the first thing I should mention is that this is joint work with Martin Herschel. Osamu Yama and Hiroyuki Minamoto. So I'll start very classically by just remembering what we talked about in representation theory of, say, hereditary finite dimensional algebras. Basically, look at representation theory. Hereditary finite dimensional algebras. And when we say we look at representation theory, well, the things we study are typically short exact sequences and the arc-over and stuff like that. So basically the philosophy of well, the higher dimensional representation theory is just to, instead of looking at short exact sequences, we look at d plus 2 term exact sequences. So instead of looking at elements in x1, we look at elements in xd. D-dimensional representation theory. Well, basically we just look at, so consider d plus 2 term exact sequences. So an element in xd instead of short exact sequences, which are an element in x1. And yeah, we like our global dimension to be, equal to d, because we're not that ambitious. We're trying to generalize hereditary finite classical representation theory. So we're looking at d extensions where the global dimension is d, and we're restricting to a subcategory, typically a subcategory such that all the other x, so x1 to d minus 1, vanishes. So we are really only considering xd. Subcategory. x1 to d minus 1 is 0 on the subcategory. Okay, so, well, one thing you should observe is that even though I didn't really make anything precise, if we insert d equal 1, then we're really back up where we started. So we're looking at hereditary. This condition kind of disappears because there is no numbers between 1 and 0. And well, we're looking at short exact sequences. Okay, so basically our philosophy is we understand the upper setup, well, might be optimistic, but let's say we understand the upper setup, and we want to carry as much as we can over to the lower setup for arbitrarity. Consider one fact from representation theory of hereditary algebras. We have, well, basically three kinds of algebras. They could be representation finite, tame, or wild. So we want to do the same thing d-dimensional. And for representation finite, we introduced the notion of d-representation finite algebras. So for the sake of this talk, I'll assume this step is kind of okay-ish. We've done that. So what I really want to focus on today is what has to go here, or what's supposed to, at least some examples that could go here. This is what we want to focus on today. What are at least examples of d-dimensional tame algebras? I should also maybe mention that for these together we introduced the main d-representation infinite. Algebras, so yeah. With it, yeah. If you don't care about the border between tame and wild, you could also just say we want to construct typical examples of d-representation infinite algebras. Okay, have people read the announcements? So our starting point for today is that, well, classically, tame hereditary algebras are derived equivalent to Fano weighted projective lines of Geigle-Lenzing. Classically. Algebras. They are essentially the same up to derived equivalents as Fano, Geigle-Lenzing. Weighted projective lines. Misplaced my notes. So our plan basically is generalize weighted projective lines to weighted projective PD, D-space, and hope we get D-tame algebras via derived equivalence. Okay, so I'll just tell you what weighted projective D-space is. And if you didn't know what weighted projective lines are, you really just get the exact same definition specializing d equal 1. So there's no point in me giving the definition twice. And today I just want to look at the hypersurface case. Which essentially means that there are d plus 2 weights. Okay, what we do is we start with a ring R, which is just a polynomial ring in x1 up to xd plus 2. And we factor out x1 to some number p1 plus x2 to some number p2 plus and so on plus xd plus 2 to some number pd plus 2. So these pi's are just numbers that are at least 2. We could allow 1, but then we'd essentially just have a superfluous variable and we could remove it. So okay, this. This is graded over some abelian group that's made essentially to grade this ring. So we take the abelian group L generated by symbols x1 up to xd plus 1. So for each variable we just invent a symbol. And then we have to make sure that the polynomial. Yes, thanks. And then we just have to make sure that the polynomial we divide out is homogeneous. So we ask explicitly that p1 times the symbol x1 is the same as p2 times the symbol x2 is the same as, and so on, pd plus 2 times the symbol x plus 2. Just ask these to be the same, and then obviously this polynomial will be homogeneous.
Microphone.
Yeah, what did I do? Doesn't like its battery anymore. Okay, am I back? Great. Okay, so I just invented this abelian group. Well, it wasn't really me, it was Geigle-Lenzing who invented this abelian group. And it's just made to grade this. And let's call this thing that's the degree of the polynomial we divide out C. It's just an int. So now we have a graded ring. And we can consider the categories. On LR should just be L graded R modules, or the MLR should mean L graded Macaulay modules. And in particular, we look at this category, coherent sheaves on X, where we don't really define X, we just explain what coherent sheaves on X is supposed to be, which is defined as the quotient mod LR modulo mod L0R. So we divide out all finite length. We should really think of X as the product of R, except that we have this funny gradient. And this X is what's called the weighted projective, or Geigle-Lenzing weighted projective PD. One short. Well, so I said we were in the hypersurface case with d plus 2 weights. If we had fewer weights, we could just put what some of the numbers here equal to 1, and weights 1 essentially don't matter. But then then our ring becomes regular, and what I want to do today is kind of trivial. If we had more weights, well, we could do a similar construction with more variables and divide out more polynomials, but then I can't do what I want to do today. So this is the one case that is interesting and I can say something about. Finally, the word Fano appeared up here in the correspondence between hereditary algebras and Geigle-Lenzing weighted projective lines, so we should know what Fano means. So we have this nice element omega, which in this case is just given by C minus the sum of the symbols xi. This is an element of L. And I should have remarked that L is an ordered group just by saying, well, all these symbols are positive, and everything we can make from the symbols is positive. So this omega will typically not be comparable to 0 because, well, somehow that, yeah. But we can ask, well, if we take a sufficiently high multiple of omega. So let's say we take a common multiple of all the pi and multiply this with that. Then we just get a multiple of c here. So if we take a sufficiently high multiple of omega, then it will either be bigger than 0, equal to 0, or smaller than 0.
Sorry, what is c? Could you define c?
C is P1x or P2x2 or so on.
I find it.
So yeah, I should remark this is really dualizing in the way one would expect. So this gives a seriality form x I from F to G is x dual of x e minus I from G to F twisted by omega. And now we're basically just wondering if omega is positive or negative in L. So our x is Fano by definition. If there is some number such that n times omega is negative. some sense if these xi's in total win against the c. And you can easily see that, well, basically we're thinking of our c to be more or less 1, and these xi's to be different copies of 1 over p1. So 1 over p1, 1 over p2, but if p1 was p2, they'd still be different. So this is equivalent to asking that 1 minus 1 over pi is smaller than 0. Well, and one thing you can notice, even if you didn't understand at all what I was saying now, is that the more pi's, the bigger the dimension gets, the more likely it is that this term will win, because it's just a longer sum. So somehow we have more Fano cases to take care of, and well, we hope that they still all give D-tame algebras, but we don't really know. Let's write that up as a hope, maybe here. Hope. That it acts as final. Then there is a tilting bundle. Such that the endomorphism ring is tame. And, well, since I didn't really define what D-tame is, and I don't want to do that either, I'll just say it is actually enough to find a tilting bundle such that the endomorphism ring has global dimension at most D. That's really what we need. And the fact that this is enough was pointed out to us by Lucilla and Ragabukats. So, just to explain what the words in the title mean, this is what I mean by D-tilting. A tilting object such that the global dimension of the endomorphism ring is at most D, or in this case it will be precisely D. So since I'm writing down this hope, I want to point out immediately that we can answer this positively in some very few cases. So you shouldn't take away the message that he wrote down this hope and then he was talking forever and probably proved it in the end. We're very far away from proving this in this generality. What else do I want to say? It's fairly okay to see that if we have a D-tilting bundle, then our X actually has to be final. So we really need this homological property, otherwise the homological algebra doesn't match up enough to get it right equivalence. Well, in case D equal 1, this is true. So that's really the extent of the evidence we have for this being true. at this point, you could also argue that you have the opposite motivation. So you maybe want to study some strange d-dimensional geometric objects, and typically studying the entire category of coherent shells is hopeless as soon as the dimension is bigger than 1, essentially. So you'd wonder, well, maybe we can do something along the lines of higher representation theory also in the geometric setup. And one way to get examples of nice subcategories that would qualify for higher dimensional representation theory inside vector bundles or something like that would be also to find a derived equivalence to something the same. Final remark here. What we can always do is find something that looks a bit like a canonical algebra. So we can find it for classical weighted projective lines. There's always a derived equivalence to a canonical algebra. And we get a similar thing here, but its endomorphism ring will have global dimension 2D, so that's not good enough for us. And it's the same in the classical situation, except in type A, the canonical algebra will not be hereditary, but you can find, well, in the Fano case, you can find a different derived equivalent algebra that actually is hereditary. Okay. Maybe just take a second and look at the case d equal 1 again. Look at this formula. So we have we have 3 summons here. So 1 over p1 plus 1 over p2 plus 1 over p3. We can see that if all the pi's are at least 3, then we're lost because 3 times 1/3 is not bigger than 1. So at least one of them has to be 2. And then we can, it's fairly straightforward that the possibilities are either 2, 2, and some number. If we have 2, 2, then we're already good. And some number. This will correspond to type dn tilde, or 2, 3, and then another 3, a 4, or 5, which will correspond to the 3 e types 3 e tilde types that we should get. So now we need some kind of strategy for finding such tilting bundles. And maybe the strategy starts with the following observation. If we first get rid of the line bundles, so we look at vector bundles, without line bundles. The line bundles here are just the structure shifted by elements of our group L. So we could kind of imagine that we have some control over line bundles. So our idea is maybe we can first make the tilting bundle of modular line bundles and then add line bundles as we need them. We can see that in here we have sitting CMLR underline. So where does this come from? Well, clearly we have a natural functor from graded modules to coherent sheaves, just by construction. And if we restrict the Cole-Macaulay modules, then this will be an equivalence to a subcategory. And the final observation is that projectives here, which are essentially just R shifted by an element of L, are in equivalence to line bundles here, which are just the structure sheet shifted by an element of L. So our strategy now would be, we try to first find a detilting object in this triangulated category, and then hopefully we can add some line bundles to get a detilting bundle in vector bundles over X. Somehow, yeah. I don't think we have a philosophical reason why this should work, except that we have some examples where it works. Okay, for this category, we do have a tilting object, but typically of too large global dimension, or the global dimension of the endomorphism ring is too large. So, write that down, C N L R as a tilting object. With endomorphism ring equal to tensor product over a pi minus 1 quiz. So just take lots of, say, linearly oriented a pi minus 1s, as many as we have weights, and take their tensor product. So what we observe here is that, unfortunately, well, all of these are hereditary, and if we take tensor products, the global dimensions add up. So typically we have global dimension d plus 2, which is 2 too much for our purposes. And in general, we can't do anything about it, but we might be lucky. If some weight was 2, well, then a pi minus 1 is just a1, so that's just k, and the tensor factor k doesn't matter. So we save 1. The other chance we have to save 1 is if we had a factor ka2 tensor ka2, which is derived equivalent to e4, or ka2 tensor ka3, which is derived equivalent to e6, or ka2 tensor ka, where was I now, 4, which is derived equivalent to e8. So basically, yeah, at this point we can just continue if we're lucky, and we can reduce not the whole product, but just one factor is smaller, or a product of two factors is smaller. Then C and L R as an equal object. So remember, in the beginning we're 2 off, so we need to save twice. So either we save by having a 2 and having a 2 again, or we save by having a 2 and then this A2 tensor A something that is Dirac equivalent, or we use the second trick twice, but we have to save twice. Okay, so what we want to do now is add line bundles to this in a somewhat controlled way so that we actually get the tilting, a de-tilting bundle. And to do that, we need some combinatorics. We define a map gamma, our grading group to Q. Remember, our grading group is essentially the same as the collection of line bundles. This we call omega normal, or just normal. If, well, we want it to be order preserving, so gamma x is smaller than gamma y. We wanted to play well with C. Gamma of x plus C is gamma of x plus 1. Adding C should just add 1. And the last property, which we want just if we ask for omega normal, is that gamma of x plus omega is smaller equal gamma of x. And I should explicitly point out, because this, even though this was clear to me, it confused me repeatedly, we're not asking for this to be a group homomorphism. It's just a map. It's fairly easy to make such a map. In the Fano case, we can just, well, essentially do what we're doing before and make an actual group homomorphism, sending C to 1 and sending the symbols xi to 1 over pi. But now in the next step, we want such a map gamma that actually plays well with our chosen tilting object in CM underline. What do I mean by that? Here, and well, since it's we're looking at chromopoly modules over a hypersurface, so we have a complete resolution, and we wonder which degrees or where are the various projectives in our complete resolution, and we want this to match very nicely with the gamma. So we say this gamma resolution. Let me write it like that. Look at M. We look at its projective cover, and well, this will be some sum Rx with something is, the point is, I only want x's to appear where gamma of x is 0. So basically, we take the projective cover and we look at which shifts appear here, and we only want shifts appear where gamma is 0. And similar for the injective envelope, well, the injective envelope in CN, so these are also projected. Here I only want to allow summons where gamma is 1/2. Now you see, if you look at the complete resolution, the next thing that should come is just a copy of this, but since we integrated, set up a copy of this shifted by C. So what really happens is we have everything is in degree 0 here, or it has gamma equal to 0 here, gamma equal to 1/2 here, gamma equal to 1, gamma equal to 3/2, and so on. So the complete resolution really just takes these half steps with respect to gamma. Okay, and if we should find such a gamma that is omega normal and such that M has a gamma resolution, then we're good. Here, we have M D tilting and gamma L Q omega normal such that M has a gamma resolution. Then M lifts to a D tilting one. So that's really the situation we like. But yeah, the problem now is how to construct this gamma. Somehow the strategy here is similar to what happened here. Also here we couldn't control the entire thing. We just looked at very small factors and tried to reduce there. And that's exactly what we'll do for the gamma too. Unfortunately, all other talks will have to be cancelled because I used up the microphones. Okay, so our strategy is to look at very small dimension and use tensor products. So what do I mean by very small dimension? Well, essentially we're looking at d equal 0 or d equal -1 even, because well, d was the dimension of the approach, so d equal -1 means we have a zero-dimensional ring, so just kx1 modulo x1 to the p1. That's an algebra we can control. And then, yeah, we can also look at the two-variable case. And then we have a notion of tensor products of matrix factorizations due to Yoshino. And we had to work a bit to adapt it to exactly what we wanted. But the bottom line is we can put together these tilting modules, and we keep complete control over their complete resolutions, and this will help us to find such a gamma. So we can also combine the gammas in a very simple way. Yeah. Time's a bit short to give details, so I'll just give the conclusion of this, which is basically, in these cases, it actually works. Maybe two closing remarks. The first is that really, somehow philosophically, this method is wrong for answering our original hope, because we're still only carrying over stuff that we know in very small dimension, but there's just so many more Fano situations in the higher dimension that we can't possibly hope to get everything by just carrying over stuff from dimension 1 or something like that. So this strategy gave us some examples, but it's the wrong strategy for a general result that one might hope for. The other remark is that even in these cases, the endomorphism ring of the d-tilting bundle gets somewhat complicated. So basically, we have a lot of trouble just trying to write down the quiver, and well, we haven't even properly tried to write down relations, so it gets very confusing very quickly, unfortunately. It's just lots of vertices. Okay, thank you.
You pointed out that finding gamma could be very hard, but a priori you may have more than one gamma. So if you have gamma, can you hear me?
Not quite.
Sorry. I guess you explained that finding gamma could be hard, but a priori you may have more than one gamma. You may have gamma and gamma prime, and therefore you may have two different gamma resolutions. So in that case, do you know how they're connected to each other?
So the question was, can we have more than one gamma, and how are they connected? And the answer is basically we haven't considered it. We were happy when we found one gamma.
but gamma is the one that gives your M to a d-tilting bundle. Is that right? The existence of gamma resolution is the...
Yeah, so the gamma really tells us somehow how M sits compared to the line bundles, right? So we want to choose line bonds that are somehow very close to M. But I mean, even if you look at say, classical case D tilde, you can see that we have choices for the line bundles, some choices. But yeah, I don't think we have any overview of what kind of choices you have.